Hi guys, today we're going to look at the volume of three-dimensional shapes. So before we do that, let's look at a little bit about the units that you'll be using. So just remember, whenever we're measuring in one dimension, so like finding the perimeter, the length of something, or the circumference of a circle, we're always going to just keep the units the same. So for one dimensions, the units will just stay whatever the units you started with was. So if you started with centimeters and you add centimeters together, the units are still centimeters. Then when we get into two dimensions, we began to talk about area. So to find area, you're going to end up squaring the unit. So it's the number of square units within the shape. So that means if you think about the area of the square over here, I would do side times side or length times width or base times height, which really means I'd be multiplying units times unit. So 1 unit times 1 unit would be 1 unit squared. Um, Also, if you think about it in terms of inches, inches times inches will become inches squared, or feet times feet, feet squared. Then when we talk about volume, which is what we're going to be talking about today, that's going to be in 3 dimensions. So if we're talking about volume, if I have the volume of this cube, length times width times height, or side times side times side, it's 1 unit times 1 unit times 1 unit would be 1 unit cubed. So for volume, you're measuring the number of units cubed. So if you think about in terms of centimeters or inches, inches times inches times inches would be inches cubed. So for volume, you're going to be cubing the units. So before we actually start doing some calculations, I just want to talk about a couple ideas about finding the volume. So one idea to find volume is to use cross sections. So if we're talking about using cross sections to find volume, if you just take a look at these examples to find volume of prisms, if you look at this first example, the two yellow rectangles here are congruent and they're parallel because it's a prism. So if you imagine taking cross sections that are parallel to those two yellow bases and you take an infinite amount of cross sections and then imagine finding the areas of those and then adding them together, that would give you the volume. Same thing for these triangular prisms. If you look at the cross sections, they're parallel to the bases. So if you kept doing an infinite amount of cross sections here and added them up, that would be the volume of your prism. Same with the cylinder. Take cross sections that are parallel to the two circular bases and add them together, the areas of the cross sections, and that would give you the volume. So that's kind of called the stacking idea. So you're using cross sections and then you're finding the areas and then you're adding them up. Which kind of ties into this next principle called Cavaliere's principle. And Cavaliere's principle is basically saying if I take these three 3D shapes here that look different, they would have to have the same volume because they're two shapes that have parallel bases, or three shapes that have parallel bases, and the cross sections of the three-dimensional figures are equal in area. So since the area of the cross sections are the same, and since the bases are the same, these would end up having the same volume because the heights, if you look, are also the same in the pictures. So it doesn't matter if you have a figure that's called an oblique, it's slanted, um, it ends up having the same area or same volume as long as the areas of the cross sections are the same and the heights are the same. So that's called Cavaliere's principle. So let's continue talking about this by looking at some vocab. So if we look at vocab for prisms, we've already talked a little bit about prisms, but just a refresher here, a prism is a polyhedron with two congruent faces that are the bases, and the bases have to lie in parallel planes. So whenever you have a rectangular prism, which is this picture here, this may be a cube if all the sides are equal, you really can decide what you want to call the bases. So since they're all rectangles, so if I call the bases, let's say the front and the back, those would be my two congruent faces. So I'm going to call this and the back the base. So these would be the bases. And then the lateral faces are those sides that connect to the bases. So these would be the lateral faces. So the lateral faces will always be rectangles, no matter what kind of prism you have. The sides that connect the bases will always be rectangles. The bases will change depending on the shape. So if it's a triangular prism, the bases are triangles. Pentagonal, the bases are pentagons. The next vocab word here is when we talk about the altitude or the height. So as you already know, when you're finding the altitude or the height, you always have to make sure that you're perpendicular on when you're measuring it. So it's if we're talking about a right prism, the altitude or the height, if you look at this picture, is going to be the length of this edge. So basically it's that perpendicular distance between the bases. So in a right prism, that just means that the bases are perpendicular to the sides. So the height really works as that length of the edge. Where if we have an oblique prism, which is what you saw on the previous page, basically as you take this prism and it's now slanted, the height is going to be measured on the outside, similar to that of an obtuse triangle, where you have to measure the height on the outside so that you make sure that you're measuring it perpendicular. So it's that perpendicular distance between the bases is really what we talk about when we talk about the altitude or the height. And then just a refresher, remember when we talk about naming prisms, they're named by their bases because their bases are those unique those unique faces. So that's really what makes it a hexagonal prism has two hexagons as bases. Remember the lateral faces, all of these rectangles that connect the bases, those are the lateral faces. So when we talk about the bases, that's the unique polygon, and then the lateral faces are those rectangles. So again, this here is kind of just a repeat of what was on the previous page, just with more examples here. So when we talk about using those cross sections, we kind of talked about it on the previous page. So when we're finding cross sections to find volume, you're basically thinking find the area of each cross section, and then you're going to add each area up. Or if you think about finding the area of each cross section, so if I have this stack of paper, like an 8.5 by 11 piece of paper, you want to find the volume of the stack. Well, you find the area of each cross section, which would be the same because it's just, they're all congruent rectangles. And then if you just multiply it by the height, that would find the volume because that would tell you the height. It really is telling you how many sheets of paper are in that stack. So if you look, here's just some more examples of that. So it's just saying, okay, well, if we take and we divide these prisms up into congruent cross sections, the more cross sections, the better, and find the area of those. Since they're all congruent, multiply by the height, that will give you the volume. So that's where this volume formula comes from. So on your reference sheet, you have this formula that the volume of a prism is big B times H, or capital B times H. Capital B stands for the area of the base. So in math, whenever we use capital letters in a formula, that means that you had to do some calculation to get that. So the fact that this is a capital B, not a lowercase b, tells me that I had to do a calculation to get to that. So it's not the length of the base, it's actually the area of the base. And it does say it down here, but I just wanted to write it up here as well, just so it really stands out. So in order to find the volume, it's the area of the base, which really ends up being the area of those cross sections, since they're all going to be congruent, and then times the height. It tells you the distance between the two bases. So let's look at doing some calculations with this. So again, we talked about Cavalieri's principle, where it doesn't matter if you have the oblique prisms or you have right prisms. Here's a stack of CDs to kind of show you the volumes are going to be the same, because as long as we have cross sections of equal areas and the bases are parallel, then the volumes have to be the same as long as the heights are the same. So that's basically what it's saying. In other words, if two prisms have the same height and the same base, then oblique and right prisms will have the same volume. So that's basically the idea here of Cavalieri's principle. I know we talked about it before, but it works for prisms. So when we're looking at calculating the volume of prisms, remember your formula. You can get right from the reference sheet. The volume is capital B times H. Capital B stands for the area of whatever the bases are. So in this case, I have a triangular prism, which means my bases are triangles. So now you're going to have to basically plug in your area formula for triangles. So the volume is going to be the area of the triangle times the height of the prism. Not the height of the triangle, the height of the prism. So If you think about area of a triangle, it's going to be base times height over 2. So the area of the triangle, base times height over 2, and then we have to multiply by the height of the prism. I'm going to go ahead and plug in the height of the prism right now because I don't want it to have two h's in the formula because they're two different h's. So the height of the prism is that distance between the bases. So if I have these two triangular bases, the height of this prism is going to be that distance between them. So this is the height of the prism. This is the h. So then to find the volume of the prism, it'll be base times height. So the base of the triangle is going to be 4 times the height of the triangle is 1.5 over 2, and then times 6. So remember, the 6 came from the height of the prism. So for this, you guys can really, you don't have to show all of these steps. Some of you can go right from here to the substitution. That's completely fine. Just remember that the area of the base, you're going to have, that's going to change depending on the shape. So if it was a rectangle, you would do length times width, triangle, base times height over 2. If it were an octagon or something like that, typically they're going to give you that area to use, or you could have to find it using what we did in the last unit. So for this, you go ahead and multiply those, and you're going to end up with 18. The units on this are meters, and since we're talking about volume, it's going to be meters cubed. So then if we go to the next page, there's some practice problems for you guys to do. So you're going to do these after the video, and if you don't finish them, they'll become part of your homework. So come back to these after the video as classwork/homework. So I'll be checking those to make sure that those are complete. So the last thing I want to talk about with you guys is finding the volume of a cylinder. So it's very similar to that. So let's go to this page, and then you guys should have some time to work on those practice problems. So when we're looking at volume of cylinders, it works very similar to volume of prisms, where you can think of it as this stacking principle or the stacking method. Since cylinders, like prisms, have bases that are congruent and parallel. So if you think about your cylinder, you have your parallel bases, and you could slice this cylinder up into cross sections of equal area, and you can basically cut as many slices as possible and use those areas to approximate the volume or to find the volume. So if you break this up into infinitely small, an infinite amount of circles, and then find the area, then add them up, that would give you the volume. So really what ends up happening here is to find the area of the cylinder, it's the same as a prism. It's the area of the base times the height, because you want to say, okay, what's the area of each circle, and then add them up, or the area times the height would tell you the total amount of circles that you have. So it's the big B times H, meaning the area of the base times the height. But the area of the base is a circle, and if you remember, area of a circle is pi r squared. So that's what gets replaced here. So instead of saying big B or capital B times H, the area of the base times H, we just use the area of a circle formula, pi r squared times H. Since volume, this should say volume of a cylinder, since volume of a cylinder, since the base will always be a circle, the formula for a cylinder will never change. It's always just going to be pi r squared times the height. With a prism, the shape changes for the base. It could be a triangle, it could be a square, it could be a hexagon. So the base is going to change, which is why we use just capital B times H. But for a cylinder, it'll always stay the same. It'll always be pi r squared times H, because it's always a circular base. So here's an example, a sample question from an old Regents exam that talks about the Cavaliere's principle. So 2 stacks of 23/4 each are shown below. One stack forms a cylinder, but the other stack does not form a cylinder. So using Cavaliere's principle, explain why the volumes of these 2 stacks of quarters are equal. So remember, Cavaliere's principle talks about these cross sections having equal area. So let's just go ahead and start writing it up. So each quarter in both stacks has the same base area. So therefore, each cross section has the same area. And then since the two stacks have the same height, I don't know why that did that, have the same height. We know that they have the same height of 23 quarters because the quarter is going to have the same height. So if they both have 23 quarters, well, that means they have the same height. Then the volumes are the same. So that's the idea. So the fact that each quarter has to have the same area, and that would mean each cross section has to have the same area. That means that the volumes have to be the same because the cross sections are the same and the heights are the same. The volumes would be equal. So then the last thing we're going to look at is just doing a couple calculations, and then you guys will finish these up. So on the next page here, we look at calculating. So like I said, you can think of it as the area of the base times the height, but for cylinders, the area of the base will always be a circle, so it'll always be pi r squared times h. And this is right on your reference sheet. So you don't really have to memorize it because it's on your reference sheet. And remember, your reference sheet's right in the front of your note packet. So for this first example, find the volume of each of the figures. So for the first one, it's a cylinder, so the formula is going to be pi r squared times the height. So we just plug in. So it'll be pi times the radius, which is 2.8, squared times the height, which is 3.7. Remember, the height is always going to be that distance between the two circular bases. And then you can just plug that all in your calculator, and I'm just going to round it 2 decimal places. So I'm going to write directions for that. Round 2 decimal places. So I'm not going to leave these in terms of pi. I'm actually going to put everything in the calculator and get an answer. So when you do that, you get 91.13. Units are meters, so it'll be meters cubed. And that's it. So you guys are going to go ahead and finish these up as well as those other practice problems. So these you're going to finish for classwork. If you don't finish them, it's part of the homework. So you want to make sure that you're working and getting these 2 problems done as well as the problems in the previous section, the previous practice problems, and then you'll have a worksheet for homework.